Hello. This is a simple exercise of conducting a linear regression in R using RStudio. And the dataset I have has been provided very kindly by Sue Lewis, a former PhD student of mine, who worked on the foraging behavior of the northern gannet. Here are the data. I've already read them in. These are the colonies around the British Islands. This is the population size in terms of the number of gannets. And this is the square root of that population size, because it turned out that when first plotting these relationships, the relationship was most linear when we used square root population size rather than population size itself. And here what we have is the trip duration, the average trip duration of gannets taken to go and feed and then return back to their nests. And using satellite tags, we can actually work out how far they are tending to move as well. This is their range in kilometers. But we're mainly interested in the relationship between the square root population size and trip duration. And the first part of any statistical analysis is one of data visualization. So let's have a look at what these data look like. Here I'm going to simply run the particular code we have here. The par is setting a graphical parameter such that the dots are nice, clear, filled circles. And the text is being added simply by referring to labels that the colony has been used, where it's the gannet data colony gives those simple descriptions. So here we have a relationship which certainly appears as if that as we increase the colony size, we are also seeing on average longer trip durations. So what we need to do is to conduct a formal analysis, and to begin with we will simply fit a model. The model is a linear model of trip duration by the square root of the population, and of course the data is the gannet data. Now, to put a particular line on that linear regression, we can simply use abline off that model, because the model is an object with many properties, and by simply going abline you will see that a line now, the fitted line, has formed over these regression points. Now importantly, we need to see some descriptors of this fitted model, and so we'll say summary model here. The summary model has a whole variety of statistics, but the important things are we have these estimates of the coefficients, an intercept of about 5.6, which you can see over here, and a gradient of about 0.05 there. And here we have tests for significant deviations from zero. We're typically not interested in the intercept, but of course we are very interested in whether we can reject the null hypothesis that the true population level gradient is zero. In this case, we clearly can. We can ask for confidence intervals on our estimates simply by going confint of the model, and here are the 95% confidence intervals, such that we break off 2.5% either side of the distribution. And there we have between 3 and 8 odd, and between 0.02 and 0.07 for that gradient. Now let's have a look at the analysis of variance, and of course this is just a slightly different way of seeing pretty much the same thing in terms of here the partitioning of the variability. You'll notice here that we have a significance value here, which is exactly the same as the significance value as we have there with the 101. It's just been rounded there. So what we can conclude here is that we can reject the null hypothesis that there is no relationship between trip duration and colony size, and that is because the probability of us getting that test statistic of 29 odd or a more extreme, if the null hypothesis was true, is very small, so we reject the null hypothesis. However, that rejection is only tentative until we can confirm that our model assumptions are broadly upheld. How do we examine the model assumptions? Well, just like any GLM, we can begin by looking at the residuals. Here is what I'm doing. I'm plotting residuals for the different fitted values along the line, and what we can see is that there's no evidence here of variance changing dramatically with the size of the predictor. Of course, we've got more data points here, but there doesn't seem to be any higher or lower variability overall. Well, what about the other assumptions of normality? Well, we can simply look to see whether they are effectively normal using a QQ plot if we like, and those points do appear to be relatively linear when portrayed on that quantile plot. We can, of course, ask for the standardized residuals from that model and then plot them out in a histogram, and this is what we see. It's hard to tell because, of course, we don't have very much data to go on, but we do not see evidence of a dramatic departure from normality in this individual case. Now, having developed and fitted a model, one benefit of linear regression is, of course, being able to predict outcomes for values of x that have not yet been observed. To do this, we can use the predict function, and we can predict, for example, the size of the population, the trip duration for the population of a square root of 100. Let's move back here, and what we see here is that the prediction is about 10.5, which is just along there. Now, we can also use predict in many other ways too. And one way is to look at the 95% prediction intervals for that overall relationship. Notice that we could ask questions about the predictability of the line or predictability of the data, and here I'm asking about the data. So here, using predict and this overall simple function here with regard to the prediction interval, we can plot the mat lines along this graph here to see the range under which 95% of the value of y should fall for a given value of x. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.